Welcome. In part 1 of chapter 3, we discussed the experiments that led to the discovery of the proton and the electron. In part 2, we will continue to discuss the atomic structure. In 1895, French physicist Antoine Becquerel discovered radioactivity. In the process of studying fluorescence, he observed that a uranium compound was able to emit a fluorescence even when it was not exposed to sunlight. This was a unique characteristic to the element uranium. Later on, one of his students, Marie Curie, made additional discoveries and coined the term radioactivity as the spontaneous emission of radiation or actual particles from certain unstable elements. Further experiments showed that this radioactive material was able to emit 3 different types of particles. When it was passed through a strong magnetic or electric field, the different particles were deflected by negative or positively charged plates in different manners. The particles were all attracted to the positive plate and reflected by the negative plate. Importantly, this discovery led to the notion that atoms were no longer believed to be indivisible. In some cases, particles the size of helium atoms were detected and emitted from larger atoms. The 3 types of radioactivity are alpha, beta, and gamma particles. These particles range in a variety of different sizes. The alpha particles are the largest of the particles, with an atomic mass of 4 units and a charge of +2. Beta particles are much smaller and hold a charge of -1 and a mass that's 1/1837th of an electron. And then finally, a gamma particle has no mass and no charge. Up until the early 1900s, the dominant scientific view on the structure of an atom was the Plum pudding model. In this model, the electrons are embedded in a cloud of positive charges. So, at the center of the atom, and the entire atom is made up of both positive and negative charges. In 1909, the Rutherford gold foil experiment changed and disproved the Thomson plum pudding model. In this experiment, a source of radiation, or alpha particles, was bombarded into a screen of gold foil, and then a screen of zinc sulfide was used to detect the radiation. What was discovered was that most of the particles, you could see here in this graph, the particles are sent through the foil, and most of the particles actually made it all the way through the gold foil. There weren't very many collisions. And from this, 2 conclusions came that shook the scientific community. The first conclusion was that atoms are mostly empty space, with the electrons on the outermost region of the atom. The second conclusion was that the center of the atom was a nucleus, and inside this nucleus, almost all of the positive charge and mass of the atom was evident. This allowed most of the particles to actually miss the center nucleus of the atom and pass through empty space and be obtained at the other side of the foil. From these experiments came the notion of a proton. A proton has a charge that's equal to an electron but opposite in sign, and nearly the same mass as a hydrogen atom. The protons are the positively charged matter in all of the atoms, and the nucleus of hydrogen is 1 individual proton. As the atoms grow in size, so does the number of protons grow for each atom. There was a discrepancy, though, between the number of protons an atom has and the mass of the atom. It wasn't until 1932 that Chadwick discovered the reason for this excess mass was the result of neutrons. Neutrons are a particle that have the same mass as a proton but have no overall charge. These are also found in the center of the atom at the nucleus. So, in conclusion, we have three subatomic particles. These subatomic particles together make up an atom. We have the proton and the electron, each which have a charge, and we have a neutron with no charge. The mass of a proton and a neutron is both 1, and they're both located at the center nucleus. The electron has an extremely small mass compared to the proton and neutron. It's so small that for the scope of this course, we can consider it as having no mass. And the electron will have a charge of -1. The electrons are also located outside the nucleus and orbit the center of the atom. Now we have a few definitions to go through. The first definition is the atomic number. This number is the number of protons in a nucleus, and it determines the kind of atom or which element exists as the given nucleus. Every single element has its own unique atomic number. We can find these on the periodic table, which we will look at in a moment. Overall, atoms are generally going to be electrically neutral. What this means is that the number of positive and negative charges that exist within the atom are going to be exactly the same, or the number of electrons is going to be equal to the number of protons. Then we have the mass. The mass number, or the mass of each individual element or atom, is going to be the sum of the number of protons and neutrons that are found in the nucleus. And this leads us to the periodic table of elements. In the periodic table of elements, we have a lot of important information. First, each of these columns is called a group. The number of valence electrons in each atom is determined by the group. We'll look at this more in a minute. The rows on the periodic table are called the periods. Each period has its own unique properties. On the periodic table, we also have the atomic number. This number is found at the top of each of these cubes. The atomic number for hydrogen, for example, is 1. The atomic number of helium, for example, is 2. This gives us important information about the molecule. For example, an atomic number of 1 means that we have 1 proton. Since these are neutral compounds, it also means that we have 1 electron present. And then finally, we have the weight or the mass of the element in the periodic table. When we have an element that has the same atomic number but a different mass number from another compound, this is called an isotope. Isotopes differ only by the number of neutrons present. So these are going to have, for example, these are 3 isotopes of hydrogen. All 3 of these hydrogens have 1 proton. They're all going to have the same atomic number of 1. But the difference here, in hydrogen or just protium, there's no neutrons. So overall, this is going to weigh just 1. In deuterium, we have a proton and a neutron. Deuterium has an atomic number of 1, but it's going to have a mass of 2 because of the existence of that neutron. Then we have tritium. Tritium is a radioactive form of hydrogen that contains 2 neutrons. In tritium, we're going to have a mass of 3 and an atomic number of 1. So an isotope is when we have the same atomic number but different mass numbers due to extra neutrons. We can summarize the information of a particular element using the nuclear symbol. In the nuclear symbol, we have X as the element symbol. So for example, hydrogen would be H or oxygen would be O. Then in the top left corner, we can place the mass number, and then a bottom left number corner we place the atomic number. Using the nuclear symbol, we can obtain all of the information that's necessary to know about a particular element. We can use the nuclear symbol to determine information about the subatomic particles within an atom. For example, this atomic symbol refers to a radioactive isotope of carbon called carbon-14. In this case, we have our atomic number of 6, which indicates 6 protons, and we have a mass number of 4, which indicates that there's a mass of 14. The mass number of 14 is equal to the number of protons plus the number of neutrons. If there are 6 protons in this isotope, that means we must have 8 neutrons in order to get to our mass of 14. The periodic table is considered by many to be the most predictive tool in all of chemistry. It's composed of vertical columns, called groups, and families or horizontal rows called periods. Groups or families are the vertical columns within the periodic table. These groups are going to contain elements that have similar chemical properties. This is due to all of the elements in a single group having the same number of valence electrons. We'll discuss more about what valence electrons are during the next chapter. Horizontal rows on the periodic table are called periods. Elements within a specific period actually demonstrate a wide range of properties, but they have similar traits relative to where they are on the periodic table. For example, on the left side of the periodic table, we have metallics, and on the right side of the periodic table, we have nonmetallics. The valence electrons are the number of electrons in the outermost principal energy level of an atom. These are the electrons that are involved in chemical reactions. When one atom reacts with another atom, it's the valence electrons that are interacting between the two atoms. Elements that are in a group or family are going to have the same number of valence electrons and therefore going to interact with other atoms in a similar fashion. Some of the groups on the periodic table have specialized names and traits. For example, in the first group of the periodic table, we're going to have elements that have one valence electron. This means that these elements can form +1 cation. This means that these elements can form cations with a +1 charge. On the second column of the periodic table, we have group 2, which are the alkaline earth metals. These have 2 valence electrons, which means they can form cations with a +2 charge. On the 7th column of the periodic table, we have a group called the halogens. The halogens have 7 valence electrons and can form a -1 anion. Finally, in group 8, we have the noble gases. Now, the noble gases have 8 valence electrons, and these are going to form no ions. These are the most stable form that an element can have. This is when it's called having a full octet or 8 electrons in its outermost valence shell. These are very stable elements. In the middle of the periodic table, we have the metals, the nonmetals, and the metalloids. The metals conduct heat and electricity and have examples like sodium and copper. The nonmetals have dull luster, are non-conductors, and are quite brittle, examples like sulfur and bromine. Finally, the metalloids demonstrate properties of both metals and nonmetals and have examples like silicon and arsenic.